Hello everyone, welcome to another episode of this Deep Learning with Pytorch series. So in the last few videos of this series, we generally talked about RNN and LSTM and how RNN suffers from vanishing gradient problem, and also how we also talked about how LSTM can solve that vanishing gradient problem. Right now, let's talk about a use case which generally is machine translation. So in case of machine translation, we generally use sequence to sequence modeling. So what is this sequence to sequence modeling is, right? So we pass some set of sequences, and also the model kind of outputs a set of sequences, right? So if you remember this diagram, right, so which we discussed in our previous sessions, that we have different types of recurrent neural network. So one of them is like this many to many one, right? So this is a many to many one. So if I just take this example, this is one of the example of many to many, and this is also one example of many to many, right? So in case of machine translation, we use generally this architecture of many to many, where we pass through certain sequences to the model, and then it outputs the different types of sequences in the decoder side. So this part of the model we generally call as encoder. So this is nothing but encoder, and this is where we get the output of the model, which is the decoder side, right? So in case of encoder decoder architecture, in the encoder side, for this specific example, when we are talking about machine translation, so that this can be a simple language, any language like L1, which we are passing to the model in the encoder side, and the decoder side we will expect the model to translate that language to a different language, which can be L2, right? So some examples, like if you are passing your inputs like Bengali to this model, and it will kind of translate that to English, right? So here if you see, we are not taking the output of, we are not considering the output of each of this time sequence or the RNN. So this basically each of these are nothing but RNN, right? So here also we get certain outputs, right, at every time step. So we are not bothered about that, so we will not use that. Instead we will use the hidden states, and that hidden states we will propagate to the next timestamps of the unrolled version of RNN, right? Now let's talk in detail how this sequence to sequence modeling is actually works. So as I was mentioning, in case of machine translation, so if our input language is say Bengali, then we kind of pass a sentence to this encoder side. So this part is nothing but encoder, and this is my decoder side, right? So this is the decoder side of my model. Here I'm passing a sentence, which is, if you understand Bengali, then what I am saying is Ami bhalo achi. So that means I am good, right? So I am passing each of these tokens. So at first I will split the sentence to individual word, and then that word will be passed through a embedding layer, and that embedding we will pass through the model. So AMI is converted to an embedding, which we are denoting as x0. So we will pass this x0 to this encoder side first timestamp. So that is like x0 we are passing to the RNN, and with some initial values of h0. So that we generally initialize with zero values, and we pass through this first timestamp, and that produces the output, which is h1, right? It also produces the output here also, but we don't consider that. So that the hidden state we will pass it to the next timestamp, and the next timestamp I pass my next embedding representation of the second word, right, which is bhalo. So that will be converted to embedding of x1, and that x1 will be passed to the as the unrolled version of the RNN, and we will get the second hidden state, and in the end we will pass the word achi, right, and that will be passed to the as a third unrolled version of this RNN, and then we get a third hidden state, right, which is nothing but h3. So this h3 we generally call it as a context vector, right? So this is my context vector, which is the output of my encoder side, right? So that encoder side output, or the context vector, is kind of a representation of this whole sentence, right? So this whole sentence, we imagine that is kind of encoded in this hidden vector or the context vector, right? And using that context vector, we will pass the context vector to the decoder side, and in the starting point, while training the model, we will pass as a start of the sentence token to the first timestamp of my unrolled RNN, and that will kind of produce the first word of my English language. So if I'm doing a Bengali to English translation, so that will produce I, right? So actually this RNN produces kind of logit values. So that logit value we pass through a softmax function, and that softmax function will convert the logit values to probabilities, and that again will depend on the size of the vocabulary. So we will build a vocabulary, so when we will code this in the Pytorch, this concept will be much more clear to you. But for the timing, you understand that RNN produces the output. That output passes through a softmax layer, and that softmax layer kind of with the help of the softmax output, we pick up the most probable word, and that word we like if the model is well trained, that will produce I, right? So generally we pass this I as an to the next timestamp as an input, and it produces the next output, which is Y2, right? And that is equals to am, right? And then it goes on till it produces the last sentence, or it produces a end of sentence token. So this is not the end. There will be another step of RNN where we will pass the input as good, and that good will produce end of sentence token. So at that point of time, you kind of think that your model has produced the full conversion of one language to a different language, and you will kind of stop the iterations at the decoder side. So this is tell you, like the first is we have an encoder and also we have a decoder. So in the encoder side we pass the one of the language, and in the decoder side we get a translated version of that sentence as an output. And in between we get a context vector. So that context vector is generally a representation of your input sentence of a particular language, and using that context vector we kind of try to generate the translated sentence, right? So with this, now let's go ahead and see how the code implementation looks like in Pytorch. This is the code implementation. So I have done this coding in the Kaggle notebook. I will also mention the link of this Kaggle notebook as a description of this video, so you can just go to your Kaggle account, copy this notebook, and start playing around with this. Get started. So first of all, like few regular imports for Pytorch, which we have talked so many times. Then the dataset details, right? So the dataset which I am using is that is kind of a English set of English sentences and a corresponding sentences in the Korean language. So we are building a machine translation deep learning model which will take the English sentences as an input, and it will convert to that convert each of the sentences to a Korean sentences, right? So machine translation from English to Korean. So these are like the path of my training dataset and test dataset. So we have 4 paths, 2 each for English and 2 each for Korean, right? So Y2, so we have the train and also the test dataset. So after that, like I'm creating a function to read the raw text file. Then I am reading the files line by line using this read text function. So the 4 dataset which we have, that I am reading here. Then also I'm looking at the length of different datasets, right? So we have like English trend, then Korean trend, and the English test, and also the Korean test, right? So you can also see the length of each of these datasets. Now very important thing, like which if you are working with NLP problem and you're trying to solve using a deep learning, so this data pre-processing plays a crucial role while deciding the performance of your model. Now the few things which we will do in this data pre-processing is, like at first we will try to remove the punctuation, then we will lowercase each of the sentences, and then we will remove the new line characters. Now you might ask, like, why we are deciding these steps, right? So because I have looked into the data and I have seen like there are this piece of informations which I need to pick up from the dataset and which we need to be part of my data pre-processing pipeline. That's why I'm kind of including these steps in my data pre-processing pipeline, right? So lowercase new remove of new line characters, then split the sentences to individual words, and then we are kind of building a vocabulary of English and Korean language. So this vocabulary will contain this two part. So it's like we will have an index to word and a word to index, right? So for each of the words, right? So if I was talking about the example, I am good. So if I have only this sentence, right? So this will be converted to at first index to token, right? So first like I will be 0th index, am will be one index, and good will have a value of second index, right? So you can using these two dictionaries like index to word and word to index, you can switch between these two things, right? So these are my word and this is my index, right? So using index to word, you can go from index to word, and using word to index you can switch between word to index, right? So this is very crucial when you are building an NLP solution using any deep learning framework, right? So once that you create these two dictionaries, then what you will do is we will do the encoding, and you will also do the padding of each sentences from both language, right? So then we will prepare the training data set and test data set. So I will talk about these two things very much in detail, like what type of encoding and how why we are doing padding in the next few minutes. Let's go ahead and see what are the things. So at first I am removing the punctuations, then I am looking after removing the punctuations, I am looking at how the sentences are looking like. Then I'm just looking at the 5 pair of sentences, right? So the corresponding English and Korean sentences are given here. You can have a look at this, and then what we are doing is we are lowercasing the words, and also we are removing the new line characters from each of these sentences, right? And after that, if you just look at one of the example from English data set, this is how it looks like. So all the words are kind of splitted into individual words, and also we have like lowercase each of the words, and also we have removed the new line characters and the punctuations from each of the sentences, right? Once that is done, what we will do is we will start building the vocabulary for English and Korean language, right? Kind of looping through the at first the data sets, the English train data set and test data set. Then I'm looping through each of the sentences from this data set. At first, like we will loop through this English train data set, and then we will loop through each of the sentences, and from the sentences we will loop through each of the words. So words are nothing but I am calling it as token here. Then what I will do is I will at first check that token is available in the index to word dictionary or not. If it is not present, then I will add that token to the my index to word dictionary, right? So at first I am looping through the train data set, then I am looping through the test data set. So the steps are like uh, I will check individual words. If those words are kind of present in my index to word dictionary or not. If they are not present, then we will add the token of those words to the dictionary, right? So similarly, like we will go through the test set also, and we will similarly do the same thing for Korean data set also, right? So this is kind of index to word mapping which we are creating here. So once that is done, we will kind of dump those dictionaries as a pickle file for future use, and in the second step what we will do is we will create the word to index, right? So we will kind of loop through each of the indexes, and we will get back the token. We will create a mapping of token to index, right? So which will give us back the word to index mapping, right? So if I just look at this, so using this Korean dictionary, like an indexed word, I'm just at first I'm checking what is the corresponding word which is present at the seventh token, right? So I'm getting this word, then I'm using that word, I'm checking what is the corresponding index, right? And we are getting back the 7. So this is where I am passing my index and I'm getting my word, and using that word I'm getting back the corresponding index. So this is kind of a verification which we are doing to check if our word to index and index to word dictionaries are kind of working fine or not. So this I have checked for Korean, then I have also checked for the English index to word and word to index if they are correct or not. So this is kind of working fine for this inputs, right? So after that, I will do is I will check what is the average sentence length in the training set data set for both of the sentences. So the highest value which you can see, which I can see, is for English sentence the average length is 17, and for Korean sentences the average length is 12, right? So I am deciding as a common value which is 25 as a sequence length, just to be on the safer side, so that we do not like truncate the very large sentences to a smaller length. I'm just taking a value which is 25, and what we will do is we will convert each of the sentences to this sequence length 25, right? Now what I am doing here is I'm creating a function, right, which is like a encoding and padding. So this encoding and padding, what it will do is it will at first check. So in this step I will check if the length of the sentence, right? So the sentence which we are sending to this function, right? So we are sending values like sentence, the vocabulary, and also the max sentence length. So we have decided the max sentence length is 25, right? So we will, like, if I take this example of like I am good, right? So what we will do is we will start this sentence, we will add a SOS, which is start of sentence token, for every sentence in this data set. So we will start every sentence with this, then we will check if the length of this sentence is less than 25 or not. If it is less than, then we will pad uh, this padding tokens for the rest of the size, right? So if my the sequence length is 25, so one of the token is for uh, start of sentence, and in the end we will also have a end of sentence token, right? And in between we will have padding tokens. So how many times we will pad, how we will decide, we will check if the length of the sentence is less than 25 minus 2. So why 2? One is for SOS and another is for EOS, right? So that's why I am checking if my length of sentence is uh, less than max sentence length minus 2 or not, right? If it is less than that, then that many padding we need to do. So uh, we will check the differences of length, like 23 minus the actual length of the sentence, and the difference value we will like pad those many times of the difference of these two items, right? Then we will encode those. So using this vocabulary we will pick up the corresponding ID, and we will kind of get the IDs for each of the sentences, right? So we cannot pass my word as an input to the model, right? We need to have a numerical representation. So this numerical representation is, we have built the vocabulary, and for every word we are going ahead into the dictionary and checking what is the corresponding ID for those words, and using those ID we are encoding this each sentences. And in the end what we are doing is we are kind of adding a SOS token, then the encoding of the sentences, then an end of sentence token, and in the end we are adding the number of pads or the padding tokens we have to add. Similarly, which are like very large sentences, we are kind of truncating those sentences using this, and then we are returning this SOS plus encoding plus the EOS token, right? So because we are not padding these sentences, because these sentences are already exceeding the maximum sequence length which we have decided as 25, right? After that what we are doing is we are preparing our training dataset and test dataset, and once we have that, what we will do is we will create the tensor dataset and the data loader. So I am mentioning the batch size equals to 30 here. Then I am creating my encoder RNN, right? So we will have two networks, which is like encoder and decoder. So first we will create the encoder RNN. So in the encoder RNN, the general steps are like we are sending input size along with the hidden size. So with the help of input size and the hidden size, we are kind of creating an embedding layer at first, and with that output of those embedding layer is going to this RNN layer, and in the RNN layer we are passing this hidden size and the hidden size, and also we are mentioning the batch size equals to true, right? So the output of the RNN will be hidden size comma hidden size, right? So once we do that, then we will have the corresponding forward function. So in this forward function, what we are doing is we are kind of passing our input to the embedding layer, and we are getting the embedding output of that. Once we have the embedding output, that we are passing through the RNN output, right? And once we have the RNN output, that we are returning from the forward layer, right? So if you remember, in our encoder architecture, we have different version of the RNN, and these are like unrolled version of RNN. And if you remember, we need to pass through a initial layer, initial input, which is initial hidden layer as an input to the RNN, right? So that we are creating here. So we are creating a set of values of 0 by mentioning this shape of the this initial hidden state, and that we are passing to the first RNN layer, so that we will use when we will build the training loops, right? So after that, what we will do is we will create the decoder RNN, right? So decoder RNN, we have the embedding layer, then also we have the RNN layer, and as I was mentioning, in the decoder side we will have a linear layer which will convert the RNN outputs to a vocabulary size, and once we get that, we pass it through the softmax layer, right? So with the initial hidden layer, because we are passing the context vector, right? So we, in the decoder side, so this is like decoder. So here at the encoding, after doing the pass through the encoder layer, we get the context vector, right? So that context vector, we will pass it through the decoder layer, right? So these are my decoder unrolled version of the decoder, and we will get this, and we are getting the output, and that output we are passing here in this way, right? So once we do that, so that's why we don't need the initial hidden layer method here. So we will ignore that, as we are passing the context vector as an output, as an input to the decoder layer. So after that, we are mentioning the hidden size, then we are initializing the encoder RNN, decoder RNN, and we are creating the loss function here. Then we are creating the optimizer for each of this encoder and decoder, because both of these architectures will be trained, right? Then we are kind of looping through the training loop we have. So we are mentioning epochs equals to 5, and we are looping through the training data set, right? So at first, what we are doing is we are looping through the training data loader, and at first we are getting the initial state of my encoder hidden state, and then we are sending that state to the device. Then we are getting the input tensor, which is nothing but we are getting from the batch, right? So using the first, like batch 0, we are getting the input tensor, and we are also getting the target tensor, right? So after that, few regular steps, like we are clearing out the gradients, then we will enable the gradient calculations, right? So here we are at first passing our input tensor to the encoder, and encoder is kind of producing the encoder output and the encoder hidden, and this encoder hidden is coming from the zeros of like zero values, which is coming from the encoder layer init hidden function, right? If you remember. So that we are passing here, and we are getting the encoder output and hidden. Then we are creating a placeholder to capture the decoder outputs, right? So once we create that placeholder, then what we are creating is we are creating a batch of SOS token which we will feed as an input to the decoder, right? So if you remember, this is like, if this is the first step of the decoder, we are passing a SOS token, and also we are passing the context vector, right? This is my context vector. So if you check here, I'm initializing the decoder hidden equals to the encoder hidden. So this is nothing but my encoder hidden, right, which is the context vector that we will pass as an input to the decoder. Then I am looping through a predefined set of target length. So this is actually required. So in some of the cases during the initial training phase, you will not get the end of sentence token. So using that end of sentence token, you can terminate the output of the decoder, right? So you may not get the end of sentence tokens because your model is not trained well. So we define a predefined values through which the decoder will be unrolled, and you will keep on getting the output till that phase, right? So in the decoder side, we are passing the decoder input, which is nothing but the context vector. So this is my context vector, and this is the decoder hidden, which is nothing but the SOS tokens, right? Then we are kind of getting the output of the decoder, and we are selecting the best word out of this using the argmax 1. And once we have that, we kind of get the unsqueezed version of that, which is the current best word, and we are kind of adding those values to the placeholder, right? So after that, we are calculating the loss. We are also using gradient clipping just to tackle the vanishing gradient problem, which is very common to any of this RNN or LSTM based models. Then we are calculating the loss, right? So with that, we will see that the model loss is kind of getting decreased with every epoch, and in the end, this is how the plot looks like, right? So you can see, like, after a certain stage, your in this encoder decoder architecture has almost stopped learning, and we will talk about this problem in the next video, why this has stopped learning and why the outputs are not optimal in the next video. So after that, what we will do is we will make predictions, right? And while making predictions, we will use the encoder and decoder, both the models which has already been trained, and we are uh, using this make prediction function. We will get the output, and we are just making few of the predictions here. So using this make prediction function, and we can check the translated prediction and actual sentence values, right? And in the end, just as a parameter for you, like we generally use blue score to calculate how the model is performing for this sequence to sequence models, and we can see the blue score is around 11.16, right? So with this, this is already a long video, so but I hope you got the understanding of the sequence to sequence model, how this works. Actually, this is very frequently asked in interviews also, how the sequence to sequence model works, because this is kind of a building block for the attention mechanism, right? So once you understand this sequence to sequence model very much in detail, the understanding of the attention mechanism using RNN is much more easier for you, and you also can explain why we need the attention mechanism, right? So with this, I will end this video. In the next video, I will talk about how we can solve some of the problem of this sequence to sequence architecture. I hope you like this video. It takes a lot of effort to create this type of video. Please like this video if you found this useful, and also share this content with your friends and colleagues, which will kind of works as a motivation for me. Thank you. See you in the next video of this tutorial series.